Good evening, everybody. Good afternoon. My name is Angela Pasquale. I'm a professor at the University of Lorraine in France. I'm very honored to host to be a moderator for this afternoon for section 7, Lit Theory and Generalization. We are in room number 5. The first speaker today is Professor Tasho Kaletha. Professor Tasho Kaletha is professor at the University of Michigan and received his PhD from the University of Chicago in 2010 under the direction of Robert Kottwitz. After graduation, he was a Veblen Research in Structure at Princeton and at the Institute of Advanced Study. Then he was assistant professor in Princeton, Benjamin Pierce Fellow at Harvard, and then he joined the University of Michigan in 2016. His research interests are harmonic analysis and representation theory or locally compact groups, the Landau programs and the endoscopy and the stable Arthur-Selbert trace formula, and also Galois cohomology. So tonight, this afternoon, he will give a talk on representation of reductive groups over local fields. And it is a recorded talk from a conference, an overlay conference that took place in Singapore. So we will listen Professor Kaletha's talk. Thank you.
Our first speaker, Tasho Kaletha, received his PhD at the University of Chicago under the advice of Robert Kottwitz in 2010. Since then, he's been a member of Princeton University and the Institute for Advanced Study, Harvard, and currently he's at the University of Michigan, as you can see from the slide. He has his broad interests, I would characterize as having to do with the Langlands program in the broadest sense one could, if it's not already broad enough. He has received a number of recognitions for his work, Simon's Fellowship, von Neumann Fellowship, a Sloan Research Fellowship. Well, maybe without further ado.
Well, thank you very much for the introduction, and I feel really honored and humbled to speak in the International Congress of Mathematicians, and I'd like to express my gratitude to the IMS for their generous hospitality and to the organizers of this workshop for giving me the opportunity to deliver this lecture in person after 2 years of Zoom lectures. This is definitely a welcome change to see actual people rather than squares of heads. So what I want to discuss is quite generally representations of reductive groups over local fields. This is going to be a colloquium style talk, so the experts are going to see many familiar things. I hope that this will evoke more the feeling of comfort rather than boredom, but this will be seen. So I want to start just with a little bit of history. Group theory emerged in the 19th century from a number of different sources, but two that I want to emphasize were, on the one hand, arithmetic, when Galois studied the symmetries of polynomial equations and encoded them in groups. These groups were finite, or they could be packaged into larger topological groups that were profinite, and in particular had a totally disconnected topology. And on the other hand, groups also came from geometry, when Felix Klein was trying to classify different kinds of geometries that had emerged, like Euclidean geometry and hyperbolic and spherical geometry. And his idea was to consider the isometry group of a geometry and to use that to classify the geometry. And in modern language, we would say that the geometry is a Riemannian manifold, And if you take the isometry group of a Riemannian manifold, what you obtain is a topological group whose topology is smooth in the sense that it comes from a differentiable structure. And in particular, it's locally connected. So it feels quite different from the totally disconnected topology of a more arithmetically inclined group. And the field of automorphic forms began to establish a bridge between those two different kinds of groups. The prototype of an automorphic form is a modular form, which is a function on the upper half plane that I've denoted here by H, the set of complex numbers with positive imaginary part. And the properties of a modular form imply that it has a Fourier expansion. And it turns out that the Fourier coefficients have arithmetic significance. They're arithmetically interesting numbers. For example, the Fourier coefficients of powers of the Jacobi theta function encode different ways in which you can write an integer as a sum of perfect squares. And using these Fourier coefficients, one can form an L function, much like the Riemann zeta function. And this squarely puts modular forms into the realm of arithmetic. On the other hand, if we consider the isometries of the upper half plane is one example of a geometry in the sense of Klein. It's a model for the hyperbolic plane. The orientation-preserving isometries are the Lie group SL2R. And this group acts transitively on the upper half plane, which means we can pull back a modular form and think of it as a function on SL2R. And this function actually ends up being invariant under a certain discrete subgroup called a level. And the most interesting of these functions, the so-called cusp forms, become square integrable functions on this quotient. And what is interesting about that is the space of square integrable functions is a vector space with an action of SL2R. So it's a representation of the Lie group SL2R. And this is how representation theory enters the picture, and tools of representation theory can be used to study these objects of arithmetic. There is a useful shift in language, useful because here the vector space depends on the level, and we may want to consider one single vector space for all levels, and that is accomplished by the adelic language, where we switch from this single quotient to a double quotient of the group SO2A by the group SO2Q, and now the level is encoded on the other side, but it's really this quotient and its L2 space that we'll be interested in. And the adels are the product of the real numbers and the p-adic numbers for all different primes P. And for people working in representation theory of more different nature, they may not have thought about the p-adic numbers. So here is a very quick introduction. The real numbers are a topological field, a field with topology where the field operations are continuous. And the same is true for the p-adic numbers. And both of them contain the rational numbers as a discrete subfield. Both topologies are locally compact, which allows us to perform analysis like series and sequences, convergence and integrals. But much like the distinction above for groups, one of the topologies is locally connected, whereas the other one is totally disconnected. So this was roughly the historical development, which motivates then the following questions and conjectures. Some of the motivating questions would be, if we think of, say, modular forms as representations of the group SO2R or maybe SO2A, then we want to classify all the irreducible representations of those groups, which are the building blocks of such representations. Here I've used uniform notation for R and QP by the symbol V, which could be either a prime number or infinity. Would like to decompose the L2 space as a representation of G cross G acting on the left and the right, and would like to decompose the L2 space of this quotient as a representation of GA acting on the right. So these are some basic motivating questions. Now, in addition, Langlands continued the bridge that was started by modular forms or automorphic forms between Lie groups and profinite groups. And he was able to construct for any automorphic representation an L function, much like the Hecke L function for a modular form. And then he conjectured that any L function coming from number theory should be just an example of this particular L function. In particular, so that should apply in particular to the L functions associated to Galois representations by Artin. And in this way, we have really now connected the profinite groups to the Lie groups. So this motivates the following further conjectures that we should be able to associate to an irreducible representation of GQV a representation of the Galois group of QV, or slightly more accurate in a technical sense, a representation of the Wedelin group, which is valued in the L group of the reductive group G. And there should even be another piece of data which is going to be important, especially for global applications. And one should be able to associate to an automorphic representation, a representation of the Galois group of Q such that the L functions match. This shouldn't be literally true for any automorphic representations. There are some properties that one requires, but I'll skip those. And finally, one should be able to compute the multiplicity of automorphic representation in the L2 spectrum using this object rho that is made up from these objects here, which is how they become interesting. Okay, so these are some motivating questions. Now, what kind of results toward these questions were obtained? So first, let's talk about results from the 20th century. The classification of irreducible representations of GQV was undertaken by Harish-Chandra and Langlands. Harish-Chandra introduced the concept of a parabolic induction, and Langlands used it to reduce the classification of all possible representations to that of tempered representation. This is the famous Langlands classification theorem. Harish-Chandra further reduced the classification of tempered representation to that of discrete series representations, and those turned out to then be the core kind of representation that is to be classified. This is the theory of the R group. And as far as the L2 space, let us remind ourselves of the famous Peter Weil theorem about compact groups, which expresses the L2 space of a compact group as the Hilbert direct sum of an irreducible representation tensor its dual as the sum runs over all irreducible representations. Harish-Chandra was able to generalize this theorem to any reductive group over a local field, where now the Hilbert direct sum becomes a Hilbert direct integral, and there is a measure called the Plancharial measure. And one of the principal achievements of Harish-Chandra was that he was able to explicitly describe the Plancharial measure. So it was not just an abstract measure. First of all, he showed that it was supported only on the tempered representations. And secondly, he gave an explicit formula for it. In terms of a basic constant, an object here associated to the discrete series representation in whose parabolic induction a tempered representation occurs. This is the formal degree, similar to the dimension of a finite dimensional representation, and then Harish-Chandra's mu function. And if you see, those results hold for any QV uniformly, and this prompted Harish-Chandra to formulate the so-called Lefschetz principle, which says that the representation theory of GQP and GR ought to behave in similar ways, despite the fact that the fields QP and R look very different. And in particular, then the actual groups GQP and GR also look very different. Then Harish-Chandra continued to classify the discrete series, but only for the group G of R, only over the real numbers. And the classification there is that a discrete series representation corresponds to a triple, where S is an elliptic maximal torus, which means compact modulo center. Theta is a character of this maximal torus. And this B is a Weil chamber in the root system for this maximal torus, which contains the differential of this character. Now, as you may know, this differential here is going to actually be regular almost always, and hence be contained in a unique Weil chamber. So for almost all representations, this Weil chamber is redundant, and the representations are then described simply by pairs of an elliptic maximal torus and a character on it. Moreover, Harish-Chandra was able to compute the character of such a representation, and here I've given the formula for elements of the torus S. There is a sign in front, and then there is a sum over the Weil group. And in the numerator, we have the character, and in the denominator, we have what is called the Weil discriminant, which is a product over positive roots. So this is the picture over the real numbers, and Harish-Chandra really wanted to also classify the discrete series over the p-adic numbers. But unfortunately, despite some very important theorems that he proved, the real results about discrete series for p-adic numbers we're going to await contributions from mathematicians after Harish-Chandra. And this puts us basically in the 21st century. where now the results are not complete, so the problem of classifying the discrete series for periodic groups is still open, but we have very strong partial results already. So around the turn of the century was the work of Moy and Prasad, who defined the notion of depth. The way they did it is they defined filtrations, descending infinite filtrations of the group GQP. And then depth is simply how deep in such a filtration do you have to go before you see vectors fixed in the representation fixed by the filtration subgroup. And then they considered supercuspidal representation whose depth is 0, which means they're associated to this very top part of the filtration. And they were able to classify them by showing that such representations occur as a compact induction of a representation sigma, which is really a representation of this group. And this group is, a quotient of this group is a finite group of Lie type. And they demanded that this representation of this finite group of Lie type be cuspidal. And in turn, cuspidal representations were studied very heavily by Lustig. So in some sense, we have a very good understanding of supercuspidal representations of depth 0. For positive depth, Jeff Adler and JKU around the turn of the century gave a general construction that produces supercuspidal representation of arbitrary depth. And the way it works is that it takes as an input certain quite complicated datum, and then it produces an irreducible supercuspidal representation. This datum consists of a tower of reductive groups and a sequence of representations of those, where the first one is a depth 0 supercuspidal representation of the smallest group. Those we believe to understand by the previous block. And the others are very simple. Those are just characters, one-dimensional characters, so group homomorphisms of each of those groups into the complex numbers. And there is, of course, a list of technical conditions. And, oops. Now we have this construction, and the obvious first question is how many representations does it produce? And that was the results of Julie Kim and Jessica Finsen, who explained to us that, in fact, all supercuspidal representations are produced this way, provided P does not divide the order of the Weyl group. This is the strong form of the statement due to Finsen, and that was published just last year. Then, once we know that this map is very often surjective, the next question is, what are the fibers? And those were described by Hakim and Murnahan, who defined an explicit equivalence relation on the set of data and proved that the fibers are precisely the equivalence classes. And then there was a final hiccup. It turned out that there is an error in use construction. After 20 years of using it, people realized that there was a mistake. And there were two ways to fix the mistake. One was to remove all the wrong theorems from the paper and replace them by different theorems. And the other one was to change the construction. This was done by a joint work of mine with Finsen and Spice. Change the construction in such a way that the wrong theorems became correct. And this turned out to be important for some applications for which these theorems were important. They have to do with intertwining numbers and the like. So now we seem to have some form of a classification of at least the supercuspidal discrete series. But it looks very different from the classification given by Harish Chandra. It looks much more complicated. We have this complicated data up to a complicated equivalence relation. And if we remember the Lefschetz principle, you'd ideally hope for some kind of classification that seems close to the one for real discrete series. And in order to do this, let's look at the little definition. Supercuspidal representation you can think of as being most of the discrete series representation in some sense, but I would like to restrict attention even further to a certain very large collection of them that I'm going to call regular, and then a slightly larger collection whose significance will become important a little bit later, that I'm going to call semi-simple. And I'll define both at the same time. A supercuspidal representation is semi-simple or regular if, first of all, it arises from use construction, which we know is automatic when P does not divide the order of the Weyl group. And secondly, remember that in use construction we had a sequence of representations, the first one being the depth 0 supercuspidal representation of the smallest group, and that corresponds to a cuspidal representation of a finite group of Lie type. Well, we demand that this cuspidal representation sit in a Lustig series that is either regular or strongly regular. So those two notions are, of course, very close, which means that semi-simple and regular are also very close. And then it turns out that we obtained the following classification, which is a result of mine from a few years ago. The regular supercuspidal representations are parameterized precisely by pairs of an elliptic maximal torus and a character. And the character is supposed to be regular, which is a certain root theoretic explicit condition. And so this looks exactly like the Harish-Chandra classification of real discrete series, at least those for which the differential of the character was regular, and this is a very similar condition in some sense. Now, the semi-simple ones are classified by similar data. There is one additional piece there, rho. First of all, the theta can be slightly more general. This NS stands for non-singular. Another explicit root theoretic condition, which is just a little bit weaker than regularity. And then this rho is an irreducible representation of the normalizer of the torus, at least the part that fixes theta. And which such that when restricted to the torus, it's theta isotypic. Now, this projection up there is completely canonical, whereas this projection at the moment depends on normalizing certain geometric intertwining operators in the Lineus theory. And I believe that there will be a canonical normalization, but at the moment I don't have a canonical normalization. I only have an existence result for a normalization. So there is a slight ambiguity in this projection here. Now, the next part of Harish-Chandra's result concerned the character formula. And character formulas for supercuspidal representations were studied for a number of years by Adler, DeBacker, and Spice. And I want to present here a form of the character formula, again from my joint work with Vincent and Spice, which takes the following shape. Now, it's a little complicated, so I don't want to go through all the details. I just want to point out some qualitative features. There are certain roots of unity in front. There is a sum over a double quotient. And then the element gamma contributes in two different ways. It gets broken up into a prime to p part and a pro p part. And the prime to p part contributes by going into the character theta, that's part of this datum, and a certain function here that I'll discuss in a second. And the pro p part gets fed into a Fourier transform of an orbital integral. But remember that in the situation of Harish-Chandra's theorem, we focused on particular elements that were just in this torus S. So what happens if we specialize to that situation here? Well, the formula considerably simplifies and takes this form, where now we have the roots of unity in front. The sum is again over the Weil group. We only have the character, and this delta here turns out to play the same role as the Weil discriminant played for real groups. In fact, not only does it kind of philosophically play the same role, but what turns out to be is that this whole formula makes perfect sense over the real numbers. All of its terms make perfect sense over the real numbers. When you specialize them to the real numbers, you get exactly Harish-Chandra's character formula back. In other words, we have now restored the Lefschetz principle among large classes of the discrete series for real and periodic groups, namely those that we may want to call regular. Now I want to switch, and so this was general results about representations of reductive groups over local fields, but now I want to discuss what this implies about the local Lineus conjecture. First of all, let me recall the basic form of the local Lineus conjecture, and that means that it simply says that there should exist a finite to one map from the set of irreducible representations of G to the set of Lineus parameters, the set of Lineus parameter being homomorphisms from the Weil-Deligne group to the L group of G that we already discussed in the first slide. And this map should satisfy a number of properties, but what is interesting about these properties is that they do not give a unique characterization of this map. So in some sense, we're striving for something that we don't know what it really is. And what do we know about constructions of such a map? Well, Langlands gave a construction for all real groups. And then the first significant result for periodic groups were the construction for GLN over local function fields by Lomont, Rappaport, Stuhler, and the construction for GLN over periodic fields by Harris, Taylor, and NER. Now, this basic conjecture can actually be weakened slightly. And this would be called the semi-simplified correspondence. There is a natural map from the Weil group to the Weil-Deligne group, and one can pull back a Weil-Deligne parameter through this map, and the result is what is called the semi-simplified parameter. So one can ask, if we cannot construct the basic correspondence using full parameters, can we at least construct the semi-simplified parameter? And this has been established quite generally rather recently over local function fields by Genestier-Leforgue, and then over periodic fields by Farg and Schulze. So this is as far as the semi-simplified basic local Lineus conjecture is concerned. But now I want to discuss the refined local Lineus conjecture. And the reason for that is that the basic form is oftentimes not enough for many applications. In particular for global applications, such as multiplicities of automorphic representations, but also for local applications, such as, for example, the Gann-Gross-Prasad conjecture. One needs a refinement, and the desired refinement is that one should have a bijective map between the representations and something else rather than a finite to one map. One should be able to address individual representations. And in order to do this, one enhances the set of Lineus parameter by adding this second component rho, which I mentioned in the first slide, an irreducible representation of the centralizer of the first parameter. Now, Vaughan in 1993 realized and described that if we were to do this successfully, we cannot just look at a single group, we should look at all inner forms together. But if we were to do that successfully, we should have to rigidify the notion of an inner form. And this was done over the real numbers in the book by Adams, Barabas, and Vaughan, where they constructed, among doing many other things, constructed appropriate rigidifications of inner forms over the real numbers. And what they used in their construction is that the Galois group of the real numbers contains a single non-trivial element, complex conjugation, so that allows you to work very explicitly with it. Whereas the Galois group of the periodic numbers is quite a bit more complicated, and so this problem remained open for a while. And in 2016, I constructed the corresponding rigidifications over the periodic numbers. And there is also, in addition to that, one can use this rigidification to give normalizations of what are called the endoscopic transfer factors, which will be part of this refined conjecture that I'm going to state in a moment. Now, this was done for field of characteristic 0, and similar results were obtained by my student Peter Dillery just 2 years ago over local function fields. So let me maybe spend a few minutes to try and explain to you what this notion of rigidification is and how it is obtained. So inner forms are classified by the cohomology of the Galois group, valued in the quotient of the group G by its center. And what Vaughan realized is that this cohomology is insufficient for the purposes of representation theory. The biggest problem is that one is dividing out here by the center. In order to obtain rigidification, one considers what is called the Galois gerp, which when one works in characteristic 0 can be simply seen as an extension of the Galois group. But when one works over fields of positive characteristic, it has to be taken in the sense of algebraic geometry as a special kind of stack, which is a gerp over the FPQC side of spec F. Whichever language you're going to use, the rigid inner forms are then going to be the cohomology of this gerp valued in G. And this cohomology surjects onto the old Galois cohomology, and in this way, the words rigidification make sense because you're picking an inner form and then you're picking a preimage here which rigidifies by adding additional data to that inner form. There is a Tate-Nakayama duality theorem that explains this cohomology in linear algebraic terms. And there is also a global version over Q together with localization maps. And this is necessary when you go on and try to stabilize the trace formula using these rigidified inner forms. So that's a rough outline of how this works. And now we can forget about it and state the refined local Lineus correspondence, which is the following. There should be a bijection between the irreducible representations of all possible rigidified inner forms of a given group to the set of enhanced Lineus parameters, which is what I set up there, except that following Vaughan, we need to use not the dual group, but its universal cover. That's a technical but important point. And This bijection should satisfy normalized endoscopic character identities, where normalized means with respect to the transfer factors normalized up there. So this is the conjectural statement. And here is one global application to automorphic multiplicities. If we take a number field or a global function field and we take an automorphic representation of it, we should be able to compute its automorphic multiplicity by a simple formula which is related to these enhancement of the Langlands parameter, this is one way in which they're used. Okay, so what is known about this? First of all, so there's two kinds of results that one can consider. One result that one can consider, or one kind of result, is when you focus on specific groups and treat all Langlands parameters for that specific group. So again, for real groups, the refined correspondence was established by Langlands and Schellstadt in the 70s and the 80s, with some more refinements in the 2010s, let's say. For quasi-split symplectic and orthogonal groups, this was established by Arthur. Now notice that this is a little bit of oxymoron. I demanded that one should use O uniforms, but here I'm only using quasi-split groups. So what I mean by this is that Arthur established an injection only for the representations of these groups into the refined parameters together with normalized character identities, but he didn't go over O uniforms. And moreover, he also has global results. He proved the global multiplicity formula that I sketched at the bottom of the previous slide. Bin-Shu extended these results to similitude groups, although his results are slightly weaker. There are some ambiguities up to character twists. Chung-Pang Mok translated Arthur's result to quasi-split unitary groups, and in joint work with Mingus, Shin, and White, we treated non-quasi-split unitary groups. So here you do get the full inner class as described by the conjecture. And Gan, Takeda, and Chan treated the group GSP4 together with its uniforms and again normalized character identities. On the opposite end of the spectrum, what one can try to do is consider a general reductive group, but then limit the kinds of parameters. So what I would like to do here is consider a reductive group subject to some very mild technical restriction, and I would like to consider supercuspidal parameters. What is a supercuspidal parameter? It's a discrete Langlands parameter that starts not on the Weil-Deligne group, but on the Weil group. So you can think of it as a semi-simple discrete Langlands parameter. And in recent paper, I was able to construct the full refined correspondence for a general reductive group that splits over a tame extension, and provided that P does not divide the order of the Weil group. And it is in this construction that one uses those non-singular supercuspidal, or sorry, those semi-simple supercuspidal representations that I mentioned. They're just slightly more than the regular ones. And why did I need them? I needed them because it turned out that those are precisely the ones that populate the L packets for discrete Langlands parameters that are semi-simple. And in my joint paper with Vincent and Spies that I've been referencing a few times, we proved the normalized endoscopy for this construction, at least in characteristic 0 and when P is not too small. Now there is a slight caveat here that's not on the slide. We were able to treat all endoscopic groups only for regular parameters, and for the remaining parameters we're able to treat some endoscopic groups but not all, so the rest are still work in progress. Now, I want to go back and discuss a little bit discrete series for real groups and introduce some ideas of Adams and Vaughan from 1992. So if you remember discrete series, generally, if you don't focus only on the regular part that I mentioned that was parameterized by pairs of torus and character, you need this third part, this Weil chamber here. And I've recalled here the structure of the character of the discrete series representation on this torus. Now we're going to do a simple exercise. We're going to take this denominator and write it slightly differently. What I'll do is I'll take a square root of the product of all positive roots, and I pull it out. Here it is. So this row is half sum the positive roots in exponential notation, and I've pulled it out. And then this is the remainder of the denominator. And then I'll take this and just put it up and glue it to this character. So here I've done this. So taken the product of the character with this E row. So what happened when I did this? Something very simple happened, that the differential of this is always regular. So this thing always determines the vowel chamber, and now the vowel chamber disappeared from the classification. So now the classification looks very nice. It's uniform, it's always a pair of a torus and a character, but with one caveat: this is not really a character of the torus because of this square root that we took here. In fact, neither the numerator nor the denominator are a well-defined function on the torus, only their quotient is. Each of them is actually a function. Oh, that's a mistake actually. The denominator is not a character, so I should say genuine functions. The numerator is a character, the denominator is a function. Both are genuine on a certain double cover of this torus called the row cover. Okay, so we improved the situation a little bit by making the classification more uniform, but we made it worse a little bit by introducing a new object, this cover. And so we're not sure, is that a good thing to do or not? Well, something interesting happens. It turns out that this cover has an L group and it satisfies a local Lineus correspondence. Okay, but the real interesting thing is the following. There is a canonical L embedding from the L group of this double cover to the L group of G, whereas this is not true for the L group of the torus. There is no canonical L embedding of the L group of the torus into the L group of G. And if you now take this, you realize that the construction of the local Lineus correspondence for real discrete series becomes a completely elementary thing. You start with a discrete series parameter for G, you factor it canonically through this embedding. By the previous bullet point, it gives you a genuine character of this double cover, and that gives you a discrete series representation, and that's the end. So it's a really simple thing. Whereas if you go back and look at Lineus's original construction, there is quite a bit of ad hoc moving back and forth, which is very technical, and you can get lost at some point. So what I want to do is I want to take these ideas and transport them to arbitrary local fields. So it turns out that, so these are two papers, one that deals with tori and one that deals with quasi-split reductive groups. It turns out that you can associate to a reductive group over a local field a certain abelian compact topological group, which you can think of as a fundamental group of that topological group here. And there is a natural extension of the reductive group by this fundamental group, which you can think of as, in some sense, a universal extension. And it so happens that the characters of this fundamental group coincide with the two cocycles of the Galois group valued in the center of the dual group. What does this mean? Imagine you take a finite order character of this group here and you do a push out. What you get is a cover of this topological group, a finite cover by, well, the image of this character, which is some finite group of roots of unity. At the same time, this object, this character gives you an extension of the Galois group by, well, the center of the dual group, but really by the whole dual group, which you can think of as an L group. And then you can prove a refined local Lineus correspondence between genuine representations of this cover and L parameters in this L group. For this, you have to assume that the refined local Lineus correspondence is true for linear groups that are closely related to G. And here comes the general application. If you start with the subgroup of the L group of G, you obtain, via this procedure, canonically the following. It's a triple consisting of a quasi-split reductive group, a character of its fundamental group, hence a cover, in fact a double cover as it turns out, and the canonical isomorphism from the L group of this double cover to the group that you started with. You can think of it also as an L embedding of the L group of this double cover into the L group of G. So in a generalization of this setup to arbitrary connected reductive, quasi-split reductive groups, I should say Adams and Vaughan had such an object over the real numbers as well, and what I'm presenting here is an analog of it over arbitrary local fields. Of characteristic 0, positive characteristic, it works uniformly. So this seems to be a rather abstract application, but I want to stratify it now into a number of concrete applications. One of them I'll leave quite vague. You can imagine that this will have implications to functoriality, because you may have a, say, Lineus parameter, or you may have some other reason to have a subset of the L group that you want to capture in a smaller group. And then you wonder, well, what's the meaning of this? Well, the meaning of this is exactly that this smaller group that you've captured it by really is the L group of some double cover of a connected reductive group, and the functoriality you're looking for is between genuine representations of this double cover and representations of G. This has applications to endoscopy. Such subgroups occur in the theory of endoscopy, and then you obtain canonical double covers of endoscopic groups, and if you try to think about transfer factors in this way, you realize that they become very natural objects. There are no auxiliary choices made in their construction, and they're just product of two natural invariants that you can write down very simply. But the final application I want to discuss is that about giving a unique characterization of the conjectural local Lineus correspondence, at least for supracuspidal parameters. And it is the following. If you start with the discrete series parameter, which is semi-simple, and P does not divide the order of the Weyl group, you obtain canonically an elliptic maximal torus, a character of its fundamental group, which is a character of order 2, and then an isomorphism, like up here or down here. In other words, a canonical L embedding of the L group of the double cover into the L group of G, which absorbs this parameter, and so this parameter ends up giving you a genuine character of this double cover, just like it happened in the situation of real discrete series. Now, what would it take to uniquely characterize the local Lineus correspondence? You need to be able to write down a formula for the stable character of the L packet that corresponds to the parameter, and here's the formula. So it's an explicit formula that has to that involves this genuine character and a function A, which I haven't made explicit, but it's an explicit non-conjectural function that you can write down. And this formula here uniquely characterizes the correspondence, and again, it turns out that if you specialize this business to the real numbers, you recover exactly the previous construction. So in other words, you have a uniform characterization of the local Lineus correspondence for semi-simple discrete parameters for all QVs, real and p-adic. So, thank you.